pick up where we left off at. Yesterday, we looked at some prereq skills from pre-calculus and how we look at parametric functions, both graphing them, eliminating the parameter, and kind of just analyzing them without calculus. Today, what we're going to look at is parametrics with calculus, which there is going to be a lot of carryover from what we did first semester. Like we're still going to be doing a lot of derivatives. In fact, we don't really do too much with integrals and parametrics. Mainly, we'll just do derivatives with parametrics in general, sometimes an integral, but mostly the derivative. So a lot of the stuff that we'll be talking about will kind of carry over, will be very familiar to you from first semester topics. The only thing that is going to be different is because there are so many different variables, there are going to be like different types of derivatives that we can find. Because we do have to remember when we're talking about a parametrically defined function, we always have the x one, and then we have a y function. And so I have like the x of t comma the y of t, whether we're thinking of it as a vector or as a set of functions. And x is a function of t, y is a function of t, but then also y can be written in terms of x. So there are going to be several things that we have to take in consideration when doing these problems. So to start off, I did want to go ahead and just talk about the different types of derivatives that we have with parametric functions, and then of course the meaning of those derivatives. dx dt is the derivative of x with respect to t. Again, when we see that parametric, we're often going to think of the parameter of t. We can think of it as time. So as time passes, basically t is increasing. That's going to be the easiest way to think about these derivatives. dx dt is going to describe the orientation of the curve. And so it basically is going to talk about the left or the right hand movement of the graph as t increases. What I mean by that, as an example, if I tell you that dx dt is greater than 0, then we know that x is increasing as time passes. So as that parameter increases, then x is also increasing. Or in kind of more general terms, we know it's going to move to the right. And then the reverse of that is also true. Like if dx dt is less than 0, then we know that that graph is moving towards the left as t is increasing. dy dt is also going to be what we use to talk about the orientation of the graph, but instead of left and right, dy dt is going to describe an up and down motion. For example, if I tell you that dy dt is greater than 0, that tells you that the y coordinate is increasing as time passes. Or basically know that this is going to move upward. So as you graph this one, as t is increasing, then this graph will be moving upwards. And basically the dx dt and the dy dt work together to talk about the actual motion of the curve. And then that brings us to dy dx, which is what we think of as the traditional first derivative. It's going to be the derivative of y with respect to x. It does represent the slope of the tangent line, just like it did first semester. The only difference is going to be how we can kind of find it. So remember, we have separate functions y of t and x of t. So the formula you want to know, how do we go from that to give us dy dx? Well, dy we're going to think of as dy dt, and dx we're going to think of as dx dt. I think you can kind of look at that and see how the dt's would cancel out, and that's how you're going to end up with just the dy over the dx. But that's going to be like the first kind of big formula that we have when looking at these graphs parametrically. So let's look at an example. What's one of the first things we did when talking about the derivative? One of the first things that we did was finding a tangent line. So let's just review tangent lines. Probably don't need to, hope I don't need to, but how do we find a tangent line? we know we have the basic formula, y minus y1 is equal to m times x minus x1. And when we're finding that tangent line, of course, we have to have the point coming from x1 and y1, and then we also have to have the slope coming from the derivative dy dx. I am going to kind of avoid like f prime and y prime notation when talking about parametric functions, just because when we say y prime, we want to be clear, are we talking about the slope of the tangent line, the slope of the curve, dy dx? Are we talking about the change of the y-coordinate with respect to t, which would be dy dt? So we are going to kind of use that notation to be a little bit more exact. So we want to find the equation of the tangent line when x is equal to 2. So the first thing I'm going to go ahead and find first is I'm going to go ahead and find the point. We know x is equal to 2. That was given. We need to figure out what y is. Well, the equation for x, again, going back to it, we see x is equal to the square root of t, the square root of the parameter t. Well, when x is 2, what is t? Pretty easy to solve. T would be equal to 4. Again, you can kind of think of the parameter as time. So we have when t is equal to 4, we can use that to find the y. The y equation is 3t squared minus 4. So plugging it in, 3, 16 minus 4, 3 times 12 are 36. So what is the point? The point we have would be 2, 36. So we have the point. After we have the point, we also want to find the slope. And here's where that new formula is going to come into play. The slope of a tangent line is the derivative of y with respect to x, dy dx. This is a parametrically defined function. So we have dy dt over dx dt. What is dy dt? That's going to be the derivative of y. So again, y was that 3t squared minus 4. Even distributing that 3 across, its derivative would be 6t. What's the derivative? X is the square root of t, so 1/2 t to the negative 1/2. Wouldn't need to simplify it, but we can. Dividing by 1/2 will become 2. There is a 6t there, and I'll bring that t up out of the denominator as t to the 1/2. Could simplify that. I'm not going to worry about simplifying it because I am trying to find the slope. We again are still using that t is equal to 4. That is what we got from the condition that we're looking at. So when t is equal to 4, we see that dy dx is equal to 2 times 6 times 4 times the square root of 4. 24 times 4, right, is 96. And that would be the slope. So now I can go ahead and use that to write my tangent line. Y minus the y coordinate is equal to the slope times x minus the x. And this will be the tangent line to that parametrically defined graph. This does occur when we have the parameter t is equal to 4. That's not as important. Do notice that the line that we write, this is in rectangular form, not parametric form. We won't really write the equation of a line parametrically. We're always going to write it in rectangular form with just x and y and without the t. And again, the only new part, I think, for the most part, besides dealing with that parameter t, is how we find the slope with that dy dx is equal to dy dt over dx dt. Questions on that problem? All right, let's think about some other things that we can do with the derivative. We have like intervals of increasing and decreasing. We have extrema. One of the more common ones that we have when dealing with parametric functions is asking when the graph has a horizontal or vertical tangent line. Let's review what we know from first semester, what this represents. We know a horizontal tangent line is when the derivative dy dx is equal to 0. A vertical tangent line would be when the first derivative is undefined because we have a slope that is vertical, or excuse me, the line is vertical, the slope would be undefined. How do we have, talking about the horizontal one first, how are we going to have a slope of 0? Thinking back to when we solved a lot of these problems, we typically had a slope of 0 when the numerator was 0, and we'll say that the denominator is just something that's non-zero. Don't want to have 0 over 0, that's no slope. But basically a horizontal tangent line is when the numerator is equal to 0. Well, thinking about these functions that are defined parametrically, we have dy dx. Where does that come from? Dy dt over dx dt. How are we going to find a horizontal tangent line? That's going to be when dy dt is equal to 0. Similar if we're talking about a vertical tangent line, we know that the slope is going to be undefined when you divide by 0. So basically when the denominator is equal to 0. So a vertical tangent line, following that logic, a parametrically defined function, its derivative dy dt over dx dt. The slope will be undefined when the denominator is equal to 0, or basically when dx dt is equal to 0. And I think that makes sense to you when you think about it. Like a horizontal tangent line typically occurs at a minimum or a maximum. And at that point, when you have a horizontal tangent line, the graph is neither moving up nor is it moving down. So it makes sense that we would set dy dt is equal to 0. Same thing for like a vertical tangent line. You're neither moving to the left or moving to the right at that instance. So it makes sense that dx dt would be equal to 0. So back to actually work out this problem, if I want to figure out where this parametric function has a horizontal tangent line, I want to set dy dt equal to 0. Dy dt, make sure you use the y coordinate 1, not the x. 3t squared minus 9, set that equal to 0 and solve. Add 9, divide by 3, t is equal to 3, so t is equal to plus or minus the square root of 3. There are no restrictions on t, like it doesn't say t is greater than 0, it doesn't say t is between like 0 and 10, so we would include both of those. Do notice the question is asking us to find the coordinates, so we've only found the parameter of where that occurs. So to finish out the problem, we just need to go ahead and plug in that parameter into the equations for x and y to have the coordinate. So plugging in positive square root of 3, we have 3 minus 2, which is 1. I have the square root of 3 cubed minus 9 on the square root of 3 plus 8, whatever that is. I'm not going to bother to simplify it. Plugging in negative 1, we still get 1. Negative square root of 3 cubed, that'll become plus 9 square root of 3 plus 8. And again, I could simplify that, but I'm not going to go too far. So I'm going to go ahead and leave it like that. And then if I wanted to find where we have a vertical tangent line, similar idea, but we want to find when dx dt is equal to 0. Well, my x is t squared minus 2, so dx dt is just 2t, setting that equal to 0. So the parameter where that occurs when t is equal to 0. The coordinate that goes with that, plugging it into the equation you have, 0 minus 2, and 0 minus 0 plus 8. We can see that our answers do kind of match up. So negative 2, 8, that is when t is equal to 0. That is when we have a vertical tangent line. We have this point up here. This is when t is equal to the negative square root of 3. That's one of your horizontals. And then we have another one when t is equal to the square root of 3. Again, this has its own applications as well. Tomorrow we'll kind of focus on using this in the terminology of like position, velocity, and acceleration. But big idea that I want you to get from this slide is honestly what we wrote up here at the very, very top of what we need to do to find horizontal tangent lines and vertical tangent lines. Questions on that slide? All right, so let's go ahead and look at the second derivative. If a student's going to mess up with calculus and parametric functions, it's going to be with the second derivative. So I am going to give you what the second derivative is not, because I think that's what you want it to be, but it's going to not be this. And a lot of students are like, hey, well, I know what the first derivative is. I know that the first derivative is just dy dt over dx dt. And that makes sense because we can see that those dt's cancel out and we have dy over dx. And so they want to say, oh, well, then the second derivative is just going to be the second derivative of y with respect to t over the second derivative of x with respect to t. And that would be very, very, very wrong. And so just don't do that. The formula for finding the second derivative is a little bit more complicated. Do you want to spend some time talking about the notation of where it comes from and then go back to the formula? So when we say let's take the derivative, again, there's the symbol, the derivative with respect to x of y, we write that as dy dx, and that represents the first derivative. So if I want to find the second derivative, one way you could write it, we don't normally write it this way, but it's the derivative with respect to x of the first derivative, or dy prime dx. Well, we know that's not how we typically write the second derivative. How do we typically write the second derivative? We're taking the derivative with respect to x of the first derivative, and that's where we're kind of using that squared notation. The second derivative of y with respect to x. And I think this is confusing, and I think that it's part of the notation's fault. That just means we took the derivative with respect to x twice. First, to do it for the first derivative, and second, when finding the second derivative. So the way that we're actually going to find the second derivative parametrically is I like thinking of it kind of in this format. We're taking the derivative of the first derivative. So that's going to be step one. Yeah, go ahead.
I got a question. Why is only the d on the top squared and not the d on the bottom?
Because I wrote it wrong. That should be squared right there.
No, but why is it that only the top one is squared, not the bottom d?
Short answer, because it's not squared. It's more of just representing that we're taking it with respect to x twice.
Oh, okay.
Because we're not saying that's d squared. That's the second derivative.
Okay.
So it's not, don't think of it as a squared. And I think that's where people mess up when taking the derivative parametrically wrong. So the way we're actually going to think about it is, so step one, we're still going to have to find the first derivative using it parametrically, dy dt over dx dt. And then to find the second derivative, and to look at what this is representing. This is the derivative of y with respect to x. So like there's no more, like it's not with respect to t, with respect to x. It's going to be given by the derivative of that first derivative, but with respect to t. And then you're going to divide it because you're doing it with respect to x. So if I'm thinking about this as steps, kind of as a second step, I'll find the derivative of that first derivative first. And then as like a step 3, I'll divide it by dx dt. And you can kind of see how this is going to cancel out, like the dt's still cancel out, but then we have the second derivative of y still with respect to x. Again, don't get confused by that squared notation. So again, here's the dy dx you'll find. You'll take the derivative of it with respect to t. It will be in terms of t. And then you're going to divide it by dx dt because it's still going to be with respect to x in how we think about it. So let's go ahead and look at an example, because I think seeing an example makes it make a little bit more sense. But again, if a student messes up something, it's going to be that second derivative. So it's definitely a formula you want to practice and one you want to review. So the example I want to do, I went ahead and did like a 2-for-1. I have a parametrically defined function with x and y defined. I want us to show that the second derivative is equal to that expression. So we'll have to go ahead and find the second derivative. And then how in calculus do we often use the second derivative? We often use it to talk about concavity. So part B, once we have it, we'll talk about the concavity. So let's find the derivative first of it. So we want to find the second derivative of that curve. Step 1, can't find the second derivative until you have the first derivative. New formula. First derivative is the easier one to find because you just want to take the derivative of y with respect to t and then the derivative of x with respect to t. dy dt, making sure you choose the y, not the x. The derivative of sine is cosine. And then we have the derivative of x. That'll be 1 minus the sine of t. And again, we're taking the derivative with respect to t, so like no implicit or anything like that. And then we want to go ahead and use that in like a step 2 to go ahead and find the second derivative. And I think of this as kind of in 2 parts. I'm going to go ahead and rewrite the formula as well. The first thing we're going to have is the derivative of the first derivative, and we're doing it with respect to t, divided by the derivative of x with respect to t. And that's the formula we're going to use for the second derivative. First part, let's find the derivative of the first derivative. What was my first derivative? It's here. That is a quotient, so we do want to use the quotient rule. So I have low d high less high d low. Draw a line, and down below the bottom squared will go. So that's the derivative of dy dx with respect to t. And we're finding the derivative with respect to x still. So I want to divide it by dx dt. What was dx dt? That was 1 minus the sine of t. So there is my second derivative, not simplified by any means. And now we just want to do algebra to show that it is going to be equal to that expression. Before I do the algebra, because that's not going to be new, any questions on where I got that expression of the second derivative from? All right, so let's try it. I'm going to think of this 1 minus sine of t as over 1, so I can multiply by the reciprocal and simplify it. So simplifying this top numerator, distributing this across, I'm going to have negative sine of t plus sine squared plus cosine squared. Multiplying by the reciprocal, 1 minus sine of t cubed. Sine squared plus cosine squared is equal to 1. So I have 1 minus the sine of t over 1 minus the sine of t cubed. Simplifying 1 minus the sine of t squared. And we have shown, yes, that that is the second derivative. Of course, the most important part here was this new stuff. And then the rest was just algebra. Questions there? All right, so let's go ahead and talk about the concavity. So we found the second derivative, and we can use that again to talk about the concavity. I did include the graph here. We're going to still do this all analytically using calculus. One, good AP exam review, and two, I think that's the better way to do it. So how do we talk about concavity? First step is we often want to find the possible points of inflection. We know that possible points of inflection can occur of one of two places. They can occur when the second derivative is equal to 0 or when it's undefined. Well, for this one, the second derivative is never equal to 0 because that numerator is just a 1, no variables there. That second derivative is undefined when its denominator is equal to 0. Take the square root, move the sign over, we get sine of t is equal to 1, which on this interval only happens in one place at pi over 2. So that's the parameter where we have a possible point of inflection. How do we find the intervals of concavity? I can go ahead and make a sign chart. The t values are going from 0 to 2 pi, and we only have one possible point of inflection at pi over 2. Factors are 1 and 1 minus sine over t squared. Kind of a boring problem. 1 is always positive. Anything squared is always positive. So on this interval, in fact, for this entire graph, this second derivative is always positive. So we know that this graph is concave up on the interval from 0 to pi over 2, and then pi over 2 to 2 pi. How do I know? Because the second derivative is greater than 0. So a good review of some sign charts and first semester stuff. Some disclaimers I will say, if you put a bracket on 0 for this problem, that would have been okay because 0 is also concave up at 0. You would also been okay if you just wrote the interval like that, whether you had a bracket on 0 or not, because the second derivative is always positive. So you could technically argue it's always concave up, except for when it doesn't exist. But the AP exam would actually give you credit for that answer. Personally, I prefer kind of splitting up the interval around pi over 2. Questions on that? All right, so let's review what we've done so far, and then we'll finish up by doing arcling. I like summarizing all the different derivatives just because, yes, it's kind of the same, but also kind of different. Both dx and dy, when we talk about dx dt or dy dt, those are going to talk about the orientation of the curve. And remember, when I say orientation, that's basically the direction. How is the graph moving? Dx dt is going to talk about moving it to the right or to the left. Dy dt can inform you if you're moving up or down. Basically, a positive dx dt is to the right. A negative dx dt tells you the graph is moving to the left. A positive dy dt moving up. A negative dy dt, that graph is moving down as t increases, or you can think of it as time passes, to put it in terms of a parametric. Then we have the derivative and the second derivative. First new formula we did, dy dx, you get it by doing dy dt divided by the dx dt. It represents the same thing it meant first semester. It's the slope of the tangent line. And then we have the second derivative, which again has a slightly different formula. It is the derivative with respect to t of the first derivative, dy dx, with respect to x. making sure you find the dy dx first, take its derivative with respect to t, and then divide it by dx dt. Questions on calculus with parametric functions? All right, one more formula I want to give you just to make tomorrow go a little bit better is going to be arc length. So we first did arc length back in Unit 8, and you had two formulas for it. If you're doing it in terms of x, and again, this is just review, so I'm going to write it down. Maybe you don't need the review, maybe you do. If you're doing it with respect to x, it looks something like that, coming from the Pythagorean theorem. If you're doing it in terms of y, everything's a y value. But you do the derivative of x with respect to y squared, and it was dy. Both of those will always give you the same value. Choose the one that's easier. We can also do arc length in parametric mode. It's going to be the exact same formula. If I remind you where some of this formula came from. So where did that one came from? In the dy notation, it came from dy dy. In the dx notation, it came from dx dx, and that's why we just have a 1, but it's basically coming from the Pythagorean theorem. Similar formula if you're doing it parametrically. I don't have an example for today. We'll do the example tomorrow. But it's still going to be the integral from a starting point to an ending point. It's still going to be the square root because it's coming from the Pythagorean theorem. Parametrically, you're always going to do it with respect to dt. So those a and the b will be t values, not x values, not y values. And the formula, I think most of you could have figured it out. Dx dt squared plus dy dt squared. Often we see this, and we'll see it tomorrow, which is why I'm saving it for tomorrow. Often we will see this for PVA problems when they're talking about the distance of a particle traveled, or even like velocity, sometimes depending on how the question's phrased. So that's what we're going to go ahead and end today's notes. I know we have about 7 minutes left, so I'm going to go ahead and make sure I give the assignment and then answer any questions you have. Same assignment from yesterday, just adding to that homework number 2. I did fix the answer key folder. I know some of the pages were missing, and all those have been fixed at this point in case you were trying to check your answers and couldn't find all the questions. If you didn't notice the answer key wasn't there, then maybe you should go back and check your answers, of course. But you have homework 1, which is the parametrics from pre-calculus. And then now I am going to assign homework 2, the parametrics and calculus. It is typed on the top of the page in OneNote, but some of the questions I am shortening because they ask you to do a whole lot of stuff that I don't need you to do. So like number 16, it asks you to find the tangent line at several points. Just do it at the first point and move on. 20 also asks you to do a whole lot of stuff. Just find the tangent line and be done with it. And then for 32 and 36, you'll see it when you get to that question. I do want the final answer in rectangular form because that's how the AP exam will phrase that question. The page 712, those are going to be some of the arc length problems with that formula I just showed you. I still know I haven't discussed the Unit 10 tests, and I promise we'll do that later this week when I have a full period back on that regular kind of schedule. Tomorrow we're going to look at parametrics and PVA, so that is going to be the most common way to think about these problems with like velocity, acceleration, position, and all of that. But other than that, if you have no questions, you are free to go and get ready for 6th period. If you need to hang back and ask any questions, then please do so.